Hey everyone, welcome back to another video by Camroom 5. In the previous video, we had been talking about the initial rate method, where we drew tangents on the graph and found out the gradient to find the rate. In today's video, we're going to be talking about the half-life, for which we know the definition already. Half-life is the time required for the concentration of reactants to become half of their original value. So it means the concentration to fall from 100% to 50%, how much time was needed. It is represented by T half. We have three different kind of reactions over here. The first one you can see on the left hand side is the zero order reaction, where the rate doesn't change at all. Whether the concentration is high or low, whatever, the rate doesn't change, so the graph is horizontal. The blue line in the middle shows a first order reaction where the rate and concentration are directly related. So if the concentration increases, the rate increases, and vice versa. The green line on the right hand side shows a second order reaction where if the concentration is doubled, rate becomes 4 times. So the rate is related not to the concentration but to the concentration of square. For first order reaction, you can have this simple formula where half-life is equals to 0.693 divided by the rate constant K. So keep that in mind that it applies to first order. Now you can see this graph on your screen where I have three differently colored lines, red, blue, green. On the x-axis, I have the time in the units of minute by 4-minute intervals, and on the y-axis, I have the concentration. The red line that has a constant gradient is a zero order reaction. If the gradient of concentration time graph is constant, if the gradient is same, that means the rate is same and rate remains same in a zero order reaction. The blue line basically shows a first order reaction where the gradient is gradually decreasing, and that is because the rate is gradually decreasing as the concentration falls. The green line shows a second order reaction where the rate does not only become slower, it becomes slower with the power square because the concentration is falling, and that is why the rate becomes immensely slower. Now consider the red line. The concentration was initially 1, and when it becomes 0.5, the time required was 16 minutes. So it took 16 minutes for the concentration to fall from 1 unit to 0.5 unit. You can say the first half-life was 16 minutes. Now from 0.5 till 0.25, it would be called the second half-life, and it required almost 8 minutes from 16th till 24th, which means for the concentration to become a further half, only 8 minutes were required. Why less time is required? Because the jump is becoming smaller. First, it was from 1 to 0.5, and then it was 0.5 to 0.25. So the half-life became smaller in zero order. If you focus on the blue line, you can see that the concentration when fell from 1 till 0.5, it required only 8 minutes. And when you see the concentration fell from 0.5 till 0.25, you required another 8 minutes. In first order reactions, the half-life remained the same. Why? Because even though the jumps are becoming smaller, the rate is also becoming smaller. So for first order reactions, I should also write that. Let's see another third half-life. You can see from 0.25 till 0.125, another 8 minutes were required. So the third half-life was also 8 minutes. Why the half-life remained same? Because the reaction is becoming slower, and that is why for first order reactions half-life is constant. If you focus on the green line now, for the concentration to change from 1 till zero point 0.5, let's say 4 minutes were required. So let me write that the first half-life was 4 minutes. Now for the concentration to change a further half, which means from 0.5 till 0.25, this time 8 minutes were required, which means from 4th till 12th. So 8 minutes were required for the concentration to become further half. So the second half-life was 8 minutes. If I see the concentration changing towards 0.125, you can see almost double, which is 16 minutes are now required. From 12th till 28th minute. Why is the half-life increasing? Because the reaction is becoming very slow. And that is why the time required is increasing. Now with this, I believe half-life idea is clear, and we shall jump to the concept of methods of determining the rate of reaction. There are two methods for it. The first involves continuous method and the second involves sampling. In the first method, which is continuous method, a property of reactants, or you can say the products, is followed, or you can see is measured with time. So with respect to time, I will measure any property of reactants or products using appropriate apparatus. What kind of properties are we talking about here? So they could be the pH if it's acid-base reaction, the temperature if it's exo-endo, the color intensity if some colored product or reactant is involved, or the conductivity if it's an ionic reaction. In sampling, what happens is, then in sampling, a small sample is taken out of the reaction mixture. So from the reaction mixture, I take out a sample at specific regular time intervals. So I will take out a sample from the main mixture and then I will titrate it. So it's titrated to find the concentration of substances. Now, let's talk about sampling a little more because sampling is a little tricky. In order to understand sampling method, let's consider esterification reaction where ethanol is reacting with ethanoic acid in a reversible reaction to make ethyl ethanoate and obviously water. So as this reaction goes on, ethanoic acid is used up, right? It's one of the reactants, it's used up. When ethanoic acid is used up, its concentration should decrease within the sample, within the reaction mixture. So what I'm going to do is, I'm going to take a beaker with 100 centimeter cube of ethanol and 100 centimeter cube of ethanoic acid. The concentration of both reactants is same, and let's suppose it's 0.500 mole per dm cube. I'm going to pipette out 10.0 centimeter cube of the sample. I'm going to put it in a conical flask at exactly, let's suppose, 5-minute intervals. In the conical flask, I'm going to transfer this sample and I'm going to put it in an ice bath. Why do I do this? Because I'm going to titrate this conical flask, but just to make sure that the reaction stops, I will put it in an ice bath and then I will titrate the sample using sodium hydroxide to see how much ethanoic acid was taken out. I can do this at multiple time intervals. So after 5 minutes, another thing will be done after 10th minute, 15th minute, 20th minute. And you can see each time less sodium hydroxide will be used up. Because as the reaction proceeds in the main beaker, the ethanoic acid concentration will be decreased. So ethanoic acid will react in the main beaker and less would be available for titration. So you can see that if less would be available for titration to react with NaOH, each interval will acquire less sodium hydroxide. So that is the sampling method. I hope this idea is clear to you guys.